Okay, guys, so our last talk for today is Alexander Andersson from Sweden. He's a principal forensic consultant at Truesec, and he has a background in red teaming and software developing.
All right. Thanks, everyone, for coming. I'm going to talk about demystifying. Well, I'm going to try to demystify cloud infrastructure attacks. So let's just start with trying to figure out what we're going to talk about. And this is a classic on-premises attack. This is actually like from a old red team exercise we did like, I don't know, 10 years ago, something like that. And what you have here is something typical like, they attack, like they compromise the DMZ and somehow jump into some kind of internal segment where they like compromise something that's joined to an Active Directory domain and find some dependencies, jump to the internal Active Directory. Eventually, maybe they hit the mainframes or whatever high-value targets the threat actor want to do. So this is like a typical kind of attack, right? What I am going to try to answer is what does this kind of attack, where you have like a full-scale attack like this, look like when we are in the cloud? So to start with, we have some bad news that there is no cloud. But jokes aside, of course, there is a cloud. Like I think it makes sense to still talk about it in terms of like we have a shared platform with APIs and the web UI and services that are standardized and so on, right? So that's sort of what we're going to try to talk about. And this investigation that we're going to follow now is based on real investigations. So like all of this is real print screens from real incidents. But of course, I can't talk about one single incident from start to stop. So it's like several different incidents combined into each other. So no one feels identified, so to speak. So this all starts with a single factor authentication. That's not good, not to have MFA, of course. But I mean, that's sort of the start, what the customer reacted on. We see that the device that they logged on, like that of that user, is registered, and it's even in the EDR platform. So, I mean, that's good. We don't really see any alerts aside from one alert, which doesn't seem relevant, and so on. We see that the customer have changed password for the user, so I guess case closed, right? They enforce MFA and then reinstall the PC just to be thorough, so I guess everything is good, right? Of course not. The thing that we forgot to add here, which is what I work as a forensic consultant, so I do forensic investigations. What I like the most is timestamps. So if we add timestamps to those events that we saw, it's another story, because we see that it starts with a password reset, and then a device is enrolled, and after that, you have a single factor logon. So that's a completely different story, right? So obviously, it's not the customer resetting that password. And we also say security info here, which we didn't really cover with a print screen, but that is a, I think, underappreciated persistence technique in the cloud, which is, you have this self-service password reset functionality, and usually you have to have like different factors to do that, and it can be like an alternative email, a phone number, so on. For persistence, the threat actor can update that, and when they want to get back into the account, maybe the investigator forgot to see that those are updated, so they still have control over the account, right? Because they can just reset the password. So let's look into that password reset, because that's the first event that we know of right now, right? And we see that the password is changed by an account called sync_something, and that points us to a hybrid setup. And there are 3 types of hybrid setups, and I'm going to go through them now because we kind of need to understand how they work to be able to figure out what happened here. So we have the first one, which is federation. Usually it's federation with ADFS, but it can be like there's many other solutions that you can use as well. And it works something like this. So the user goes to a federated app and says that I want access. And it says that, no, you need to go to Azure Active Directory, which I guess is called Entra ID nowadays. They change names for things all the time. And I guess while it still says Azure AD in documentations and some like X files and stuff are named that, still I'm still also going to mix it up if they can't keep the one name. But anyways, yes, you need to go to enter ID. And enter ID says that, no, you need to go to ADFS. So you go to ADFS, and ADFS checks with Active Directory. And if the credential is valid, then the ADFS server will sign it with their secret. And then you have that secret, which is, like you have the package which is signed. So you can go to ADFS to enter ID with that thing from ADFS. And they will give you then an application-specific token, which you can then present finally to the federated app. And finally, you're in. So that's the flow. And what we saw there was this chain of trust, right? So the federated app trusts Azure AD, and Azure AD trusts ADFS, and ADFS trusts Active Directory. So what could possibly go wrong here if you think of a compromised company? Well, one way, which we saw in like the SolarWinds attack, for example, was that if the ADFS server is compromised, you don't need to be domain admin, you just need to be local admin on the ADFS server. Then you can dump the token signing certificate and the related private keys and secrets. And with that, you can just sign your own tokens, which means that, yeah, it's not a good situation, right? Because then you sort of just fly your way into whatever you want to fly into because, yeah, you sign your own tokens as a threat actor. But this is not what we saw in this specific attack, right? We saw a password reset. That's what we're looking for. This would not be a password reset. It would just be someone who's magically authenticated. So let's talk about the second method for hybrid, which is pass-through authentication. And in that case, the user goes directly to Enter ID. Enter ID asks who they are, and they provide their username and password. And that is then sent to a queue, which is then pulled by a AD Connect server, which lies on-prem. And when they got the new thing, they will just validate that. And eventually, if it's successful, it will send a Boolean, basically, which is yes or no. So what could possibly go wrong in this setup if someone compromises that AD Connect server? Well, there are some like AAD internals as an implementation for this, and there's multiple ways to do it. But essentially, you can patch the logon user W function and say something like, you know, if I don't care about the username, but if the password is banana, then say that the login is successful. And then you have a backdoor password, can log into whatever account you want. Then again, this was not a login, right? This was a password reset. So let's move on to the third and final method of hybrid cloud, which is password hash sync. And that starts with the AAD server, which takes all the hashes from Active Directory. Basically a DC sync. Maybe you've seen that if you're a red teamer. Maybe you've done it if you're a red teamer. This is the legitimate way of using that. And so it says sure and gives all the password, and they are, of course, encoded with MD4, which apparently isn't good enough for the cloud. So it actually hashes it with SHA-256 and Assault. So like if you're dumping hashes in Enter ID, you're not going to get the like classic anti-LM hashes. You're going to get something else. But still, if you crack that, then you can get that original hash and blah, blah, blah. So at this point, Enter ID has all usernames and hashes, right? So it can authenticate stuff on its own. So it doesn't need contact with the on-premises at this point. So what could go wrong in this third variant? Well, to be able to do this, you need to have a few accounts and a few secrets, right? So you need one account which is able to do that DC sync. You need some kind of a service account, which is going to be relevant soon, but the actual account that is running the service. And you need an account in Azure who is able to write the hash for users, right? It needs to be able to create users. It needs to be able to do quite a lot of interesting stuff. Because if it doesn't have those permissions, then it's not able to sync it all the time, right? So what happens if someone steals that sync secret? That's not a great situation, right? So it's obviously stored on the AD Connect server. It's encrypted, but it's encrypted with DP API. So if you have the service account, like if you're a local admin, and then you can just run as that service account, and you can just use unprotect to get that in clear text. You can, of course, also dump the actual secret and so on, and then decrypt it offline. But this is actually what we saw in this attack. So we see that someone is accessing those, like using unprotect with that specific account to get to that sync account. And we see that after that is done, then we see that that account is used from a location where it's not supposed to be used because it's supposed to run on that specific AD Connect server, right? So, yeah, what is that account? We talked about it a bit, right? It is a built-in account, which you don't really create it yourself. It has this privileged role, which is called directory synchronization accounts. And quite recently, they actually changed this. So the specific method that I'm talking about now, I haven't tried it, but I'm fairly sure that this specific technique of jumping from on-prem to cloud doesn't work anymore. But I think this, since like a week. But I think it's still very interesting in terms of that we can use this as an example to understand how privilege escalation and some other stuff like that works in Azure AD. And this account has some roles as part of the role it has some specific permissions. And one of them is to update the owners of applications. So in Azure, you have enterprise applications, right? They are used to do a bunch of different stuff. This is one example of an application, which is like a backup application. That application is able to do quite a lot, like read all the SharePoints and read a bunch. I mean, it needs to do backups, right? So it needs to be able to access a lot of things. In particular, one interesting permission that it has is that it's able to read and write directory data. So let's think about this. The account that they stole on that server is able to take ownership of applications. Those applications are able to do a bunch of very interesting stuff, which the original account didn't have. So basically, they use that update owner to be able to escalate the privileges and then act as the application. So abusing applications like this is a very interesting way that we see threat actors escalate privileges in Azure, basically. So they take over the app, they generate an app secret, and then they use that to create their own user, which they can with the original permissions, and then they just make themselves global admin because they're able to read and write the directory. So the service principal credentials is interesting in itself. I mean, what it does is that you generate these credentials and then you act as the enterprise application in Azure. That's interesting for privilege escalation, but it's also interesting for persistence, right? Because many companies that investigate breaches, they will look for newly registered applications. But if someone takes over an existing application or like generates credentials for an existing application, that won't really show up anywhere. You will have this entry in the audit log, but after 90 days that's gone, and there's no way in the UI to list all the application secrets. So, I mean, I think there is some way like you can do it with the APIs and so on to get out like the hashes, whatever, for those. But it's a really sneaky persistence technique, right? It's very common that threat actors register new applications, but abusing existing applications, I think, is clever. So that's logged, of course. Then we also get a log for when that user that they just created is now in the global admins group. And I guess that's explains some of it, but still the device that they logged in from was enrolled in the EDR, right? That's a bit weird. And it actually turns out that the threat actor thought it would be stealthy to log on from a compliant device, so they enrolled it in Intune. What they didn't know was that the customer would then push out automatically an EDR client to the threat actor's machine. So what we see here is actually the threat actor's machine. And my colleague Hassan has a complete talk where he just talks about everything we can see on this threat actor's machine because it's sent to the EDR, right? And of course they use that machine to attack multiple different customers. But yeah, we'll get back to that. So let's start drawing that kind of graph that we saw in the beginning, right, of the classic on-premises attack, now that we're in the cloud. So the first thing we know is that they dumped secrets on the ADCon server. They then used that to take over an enterprise application. They then generated credentials to be able to act as that enterprise application, made themselves global admin, enrolled their device, logged in, added some persistence and so on. And then finally, the seventh step here, which we haven't really gone through, but that would be like, syncing data and so on, to exfiltrate high-value target data. By the way, enterprise apps is another good way to exfiltrate data, right? Because it has those permissions, and you can ask the enterprise app sync data and so on. But there's multiple ways to do that. So I guess the question that we have now as forensic investigators is, how did they get to that AD Connect server? Because they can't just show up there automatically, right? Or magically. So we see that there is a connection from an internal Jenkins server. Does anyone know about Jenkins? I guess. When I talk to, we do a bunch of different stuff at Truesec, but when I talk to the persons doing like DevSecOps and so on, they say that, yeah, it's not that many that use Jenkins anymore. It's usually like GitHub Actions or whatever that's trendy, like everyone is want to use right now. But we actually see quite a lot of companies from my end, which work with companies that are affected by breaches, that they have that really old, very important Jenkins server. They're completely like built into it because of like the developed plugins and whatever. And it's just like this massive Jenkins server that is responsible for building everything. And it's really hard to maintain it. So what's not to love about Jenkins? It has this kind of awesome feature that if you're logged in as admin, it has built-in code execution. Says it right in there in manual. So it has like it's a Groovy console, and you can interact and run OS commands. You can also run like a simple script to dump all the secrets, and guess how many secrets you have in Jenkins if you have one big Jenkins that is responsible to pull code from repos, push it to where it's supposed to run, and like all those secrets that you have to run your entire production is going to be in Jenkins, right? And that's what we saw that they did that in this case. So by carving the file system, we found this deleted file, which contains a complete dump. And actually, it has this weird format of like output format. You see, it has like class, space, colon, space, something. So we're fairly certain exactly what script they used, which it was from like an online tutorial for how to do it. So yeah, that would be the first step, right? So we have the secrets dump on a Jenkins server. Still, we get the same question, right? How did I get to the Jenkins server then? And when we look at the Jenkins server, we see that there is a rat installed on the Jenkins server. So we see that it goes through Gmail. This is nothing new, but I think it's cool just because we're talking about cloud security. Threat actors can also use cloud, and they can get a C2 as a service, as I used to call it. We talk about Gmail here, but the same principle is going to apply to, there's open source C2 channels for like Slack and Dropbox and pretty much any service that have the features needed to do this. But basically what they're doing is that they are querying from the rat. We have the rat, where the server where the rat is, and then the evil is the threat actor's C2. So it questions like, do you have any new draft for me? And it says no, and it keeps polling like that, checks for a new draft. And when the threat actor wants to communicate with the rat, it creates a new draft. And this is a bit simplified, but just so you understand the concept. So it creates a new draft with like exec uname a, which is a command they want to run. And then the rat gets that command, it executes the command, and then it adds an attachment to that draft, which is the output of the command. And then it checks for attachments, obviously, on the other side of things, and it gets the draft. When it reads it, it deletes it, and so on. So then you have like a channel where you tunnel everything through Gmail. And if you're just looking at network traffic, it's going to be kind of hard to see this, right? Especially if you're this company that we're talking about who's actually using Google Cloud, which we will get into. There's a lot of services that are talking to Google Cloud all over the place, right? And I think that's when we see this being used by a sophisticated actor, they look what services are this company using. If they're using Slack and they have Slack integrations for pretty much everything, then why not use Slack as a C2? It's going to be really, really hard to find that in the midst of all that traffic. So it's really hard to see it network-wise. On the other side, we're obviously completely blind. So we cannot see anything because it's just the threat actor accessing Gmail on their end, right? So is this the perfect C2 that is like the C2 to rule them all? Well, it got one big of a problem, right? To be able to do this, you need to persistently store the credentials to the Gmail account on the compromised server. So before we turn ourselves into cowboys and log into that Gmail account, because of course we can at least do the things that that API secret is able to do, we actually found that by collaborating with these vendors like Slack and like Google and so on, if you just talk to them and say that someone is abusing your infrastructure as a C2 and you give them evidence, they're actually really helpful in my experience. So they will provide a lot of data, as much as their lawyers accept them to, I guess. But you will get way more data that way. Plus, I don't know how the German law is, but in Swedish law, it wouldn't be legal for me to log into that account, even if I know it's a threat actor using it. And keep in mind that they're probably not using their own account, right? They have probably hacked someone else's account. And all of a sudden, by using those secrets, you're hacking into someone else's account. So yeah, that is the C2. So it still doesn't really answer how did I get to the Jenkins server, because now we're talking like code execution on the actual underlying Jenkins server. If we look at what runs there, we see that they use Docker to run jobs. And we see that some time ago, someone figured that those Docker containers need network access, because they need to be able to talk to a bunch of different stuff during the build. They need to pull dependencies and whatever. So someone put it on the default Docker network, which means that from the Docker container, you're able to access localhost where you have the Jenkins server running. So that's just like the simplest Docker breakout ever, right? They're just able to access localhost and then get access, assuming they have the credentials, of course, which we'll get to later. So next question would be then, so how did I get to this Docker container? It's not like these are just internet exposed, right? They can't just find a vulnerability and just land there. These are something that's spun up, and they're fairly isolated. I mean, they can talk out, but there's no like listener coming from the outside. So we're going to go through a few different techniques that I've seen to compromise that kind of container. And one of them, we saw this weird log with an error in the pip file. So basically, pip, you know, in Python, you use pip to sync, it's a dependency manager. So we see that it downloaded version 9999999, which is a bit weird, because this was an internal package for the customer. So it's like company name internal something and version 99999. And when we looked in the official PyPy repos, we see that someone had registered the same name and put the version 9999. So apparently, this is a won't fix vulnerability in PyPy, because they say that the extra index URL, which you can use to point to an internal PyPy repo, it's designed to be insecure. It will check the official repo, and it will check the internal repo, and it will just get the newest version. So if you want to be safe, you're going to need to use index URL, but then, of course, you need to sync the entire repo, right? Which is going to be, quite annoying to keep that up to date. So no one uses that. Everyone uses extra index URL, I guess. Or actually, I only see companies that suffer from attacks, right? So what do I know? I have a weird view of everything. But that's not it about this extra index URL. There was actually also a bug in this a while back, which is quite interesting. This doesn't have any CVE, because they just silently fixed this as a bug. But we actually saw a case where the problem is that if you have an extra index URL and it checks the official repos, it will start by doing a plain text request. And then it will get like, no, you can't talk as non-SSL with me, upgrade, and then it will upgrade to HTTPS. Problem is that we saw was that someone had compromised some infrastructure in the middle of everything, which means that it checked the first package that it wanted to download, and it says, no, you need to upgrade, no, you need to upgrade, the next one, no, you need to upgrade, and then all of a sudden it said, yeah, here's your package. So basically what they're doing is doing a man in the middle of that first HTTP request, and you basically have a remote code execution vulnerability in pip. This is a very old version. This was fixed in 2017, but since there's no CVE for it, and no one updates their Docker containers, if you look at Docker images, they are full with vulnerabilities, especially for things that doesn't really have a CVE. So it's not that uncommon that you still use this old pip version, right? And so that's way number two. It's not what we saw in this case, though. what we saw in this case is this third variant, which we're going to go into. And I mean, this sort of starts with that source code repositories have somehow become our like management plane for pretty much everything at some point. So you have these CI/CD scripts and so on that you specify like what do you want to build, how do you want to build it, and so on. And this is either done outside, but it could also in some cases be done inside the repo, right? So if you're able to change like, what's the word? If you're able to commit and push to the GitHub repo, you're able to change how it builds and so on, right? And then you can edit that, can you please print all the environment secrets in this job? And it's just going to censor them. And so you say, can you please print all those secrets, base64 encode them, and then all of a sudden you get them. So I mean, there's a lot of interesting things when it comes to this. One of them is shared runners. So maybe you are actually doing your job and you're making sure that no one is supposed to just be able to push to every repo, and you need to approval and blah, blah, blah. Then you hire this weird person that want to hack you, and they are just able to push to a repo, create and push to a repo. And that repo that they have control over, even if they don't have control over your sensitive repo, is going to build on the same CI/CD server, which means that they can push their malicious stuff, and then you sit around and wait on the CI/CD shared runner. And eventually they're going to get some secrets. So there's a great write-up about this if you want to read from this Dennis guy. What we saw in this case that we're going through, is suspicious activity in the commit logs. So we see that someone has made a push to the requirements.txt file. And instead of the package that they had there originally, it's a link to GitHub, same package name. And we looked at that package, and it's exactly the same as the original package, aside from one file, which is setup.py. Setup.py is something that's going to run during pip install. And that's the only time it's going to run, which is exactly when the threat actor wants this to run, right? Because it wants to run this as part of that Jenkins Docker job. So what that does is basically that it creates that same C2 tunnel. So they get a shell inside that Docker container. So then we have that sort of first step, right, into the Docker container. Before we go into how did it get into GitLab then, we're going to ask another question which we sort of skipped over, which is, even if they had access from the Docker container network-wise to the Jenkins interface, they still need to have that credentials, right? So how they did that is a longer story, and it starts in Google Cloud. And we're going to talk about lateral movement in Google Cloud. And assume that the threat actor has compromised one machine in Google Cloud. And what could they do? So one thing which is kind of interesting is that if you just spin up a new VM in GCP and you just do next, then you're going to get like this default service account that's going to run because every machine needs to have this service account. And that one actually has quite generous permissions, including like reading your buckets. So in some cases, actually you can, like if you're live on the machine, you can query this internal metadata, right? You have sort of the same thing for all cloud providers. It's used to be really interesting when you found like an SSRF, but now they added so you need to like provide some kind of header, so it's not that often that you're able to do that in an SSRF context, right? But anyways, you can query this if someone has compromised the machine. They can read out what does this service account, what's the permissions. So that's one way which is very interesting that you can find on a compromised cloud machine. Another one is those CLI utilities that everyone is using. So assume that you have like a fairly locked down network. It's only able to access APIs from this specific server. What's going to happen is that someone is going to remote into that server. Then they want to use like Google Cloud, the CLI tool, or you have like AWS CLI, you have AZ, and so on for the different vendors. But what happens is that they log in, they then are on that specific server, they do like a cloud init or whatever command, and they need to enter and authenticate the token, and that's going to be saved in their user profile. So if a threat actor then comes along and compromises that machine, then they can, of course, just dump whatever is in their user profile. And all of a sudden, they are inside that, that same context that CLI program is. And on Linux, it would be under your .config or whatever, right? These are all like, sometimes they're encrypted, sometimes they're plain text and so on, but what sort of a good rule of thumb is that, do you need to enter a password every single time you're using this? No. So then they're probably a reversible encryption, right? So the easiest way, like you can probably dump this in a really fancy, cool way, but the easiest way is probably just copy everything that is in that config folder, paste it on your own machine, and then all of a sudden it just works. So it's fairly easy to dump this. So, I mean, that's two techniques that I think are interesting. And like coming from this like on-premises Windows Active Directory environments, I think this is very, very interesting, because what we see is that, you know, they compromise one machine, and from there they're able to extract secrets. Maybe eventually they found something that are able to list instances, they can add SSH keys, allow their own IP to log in, and they're then able, this is what that would look like, and then they're able to log into the next machine, which is like what we're talking about here, right? Lateral movement. And when they're on that machine, they're gonna start doing the same thing, and eventually they find another credential, and then they jump to the next one. And this is what we're seeing coming back to the on-premises and Windows Active Directory and so on. This is very different from that, right? We're in Google Cloud, we're using Linux and so on, but we're seeing the same fundamental problems. Because in Windows, you have this where they compromise one machine, they dump LSAS, they dump like the, whatever they want to dump, like the SAM hives and so on, right? They use those credentials to pass the hash to jump to the next machine, they repeat the process, and they move laterally in the environments. But here we see that it's not a problem, it's not a vulnerability that we can patch, because the problem here is how we as IT persons use our systems. So I think it's quite interesting that you're not going to solve all your problems if you're using your environment improperly by moving to cloud. You're going to have the same problems probably, just in a slightly different form. So in this specific case that we're talking about, they did this. They got to one machine, and eventually they started dumping credentials, and they jumped to the next machine, and they jumped to the next machine. Eventually they found access to some buckets where they wrote backups from the on-premises environment to these buckets, and they were able to download those backups. And that's how they found those secrets to be able to log into the Jenkins console. So with that said, I guess we have one problem left, which is how did they get access to GitLab then? And the customer said that's not possible because we have MFA. And I mean, there are many ways to bypass MFAs that we see today. MFA is great, and it's something that everyone should use for obvious reasons. But, I mean, threat actors have adapted, right? So we have like adversary in the middle is really common. So like if you phish the username and password, why not just relay that to the backend service, get the prompt, relay back the prompt to the user, make them enter the MFA prompt as well, so they can just do the entire flow. They just need to add one extra step in their phishing sites. And there are, of course, like evil engines and so on that does this, have already implemented it. I think also, speaking of MFA, and in a cloud context, this becomes important, right? Because a lot of it about cloud security is about the identities that we're trying to protect. And I used to work as a red teamer, and when I phished an account, it was usually for that person at the company who isn't that great with security, who's not really aware about security. So if I then phish the username and password, then I call the person, says, hi, I'm from internal whatever, and there's a problem with your salary, but according to GDPR, you need to show me the code in that authenticator app, just so I know that you are you. And of course, they're going to just read it out to me because they don't care about security. Otherwise, they wouldn't have been phished in the first place, right? So I just call them up, ask for their MFA token, which, I mean, it doesn't really matter what method that they use because I can trigger if I need to trigger a prompt or something. Where it's like, if they have that, you need to accept this login. Then I can do that login from my end and say that, yeah, you need to click OK to, solve this problem with your salary or whatever bullshit story you come up with. So I think that it's a weird, like it's not a perfect solution because we're trying to protect people that don't want to be protected in a sense. And if they can't protect their password, why would they be able to protect their MFA token? So there are better solutions for this, and we're going to get into that. One way we see that MFA is being bypassed, which is very common, is info stealers. And there are a few of them that are quite big, and they have this like advertisements and so on. They're operated as malware as a service is a common term, which is basically that they run this thing and you kind of subscribe on credentials. So they have like the Russian market is a good example of that. So what they do is that they infect machines at scale, and they steal cookies, they steal saved passwords, they steal like autofill data, which would usually contain, credit cards and that kind of information. A lot of them are also targeting like Bitcoin wallets and that kind of thing as well. And then they have this website which is just updated all the time, where threat actors that do ransomware or something else can just go to and get credentials. So when it comes to browser secrets, it's interesting because if you have the cookie, you're inside the session, right? So you don't have to authenticate. You don't have to. It doesn't matter if they have MFA or whatever they have, right? Because you're already inside an authenticated session. And stealing secrets from browsers is fairly easy because either we talked about it before actually. GPAPI is what protects on a Windows system in, for example, Chrome. So either you can do some cool stuff and try to unprotect, and like even you can dump LSAS and get the secrets needed to do it offline, or like if you're domain admin, you can have a backup secret, but if you're domain admin, you probably don't do this, so yeah, who cares? But the easiest way is that Chrome needs those cookies, right? So Chrome must have the cookies, because otherwise you sort of lose the entire point of cookies, right? So what you can do is that you can start Chrome in debug mode, then you just send a command which is like, give me all cookies. And then it's going to give you all the cookies. So it's pretty much a one-liner to just dump all those secrets. And in a sense, it doesn't really matter how you protect these secrets, because Chrome needs to be able to decrypt them, right? So if you're local admin and you have control over the system, you're going to be able to get these. Another interesting technique is, when you're inside your corporate computer, you're probably logged in to a bunch of Office apps. And you might think, like, how does it know that I'm Alexander when I open Outlook, or that I open PowerPoint or whatever? There's actually a kind of easy way to check that, and it was someone called Mr. Docs that showed this. I think he was kind of the first to write about it. But basically, you just dump the process, and then you grep for EY, which is base64 encoded start of the GVT tokens. And of course, they need to be in memory, because otherwise you can't authenticate. That's how you authenticate, right? So basically, just do a process dump of the Outlook application, read out those GVTs, and you're in. So, I mean, that's one of many techniques that we see that they bypass MFA. However, I think we are getting slightly better at this. When it comes to, if we go back to Azure, they have some detections for this kind of thing. You might see an alert that says anomalous token. For example, my IT department might have gotten one because I was in Stockholm, and then a few hours later, my token was all of a sudden in Germany. So that's a weird movement. Then again, there was probably a gap in between there, so it's sort of the same as impossible travel in many senses, right? So if a token moves very quickly between two locations that you can't really travel that fast, then it's going to trigger this kind of alert. It's kind of good. I've seen a few false positives of this where people are just traveling with their computer. But I think that's a good way where we start to become better at detecting cookie theft and so on. Another good way is if we're talking about enrolled devices. So in Windows, you have different types of management of devices, right? So you can be like active, like the classic, you join to an Active Directory domain, but you can also be enterprise joined, or you can be Azure AD joined. And for that, you need to have some kind of super secret inside your machine, right? Which is the refresh token. So in Azure, you have this stored locally on your machine, and if someone steals that, then it's kind of bad, right? Because they can refresh that token. Because all those other tokens are usually fairly short-lived. So they can get into your account and probably sync your Outlook and download all the mails within that time. But yeah, it's going to be a short-lived token. This is more of a long-lived token. It's not infinitive, but you see the day there, expiry time of that specific one. But the thing that is good here is that Windows 11 requires TPM. And this is one of those secrets that's stored in the TPM. And to my knowledge, and I guess to public knowledge, there is no way to dump secrets from TPM. So it's actually a very good thing where we protect our secrets on a hardware level. There's also some other interesting projects, I think, going on where you have like Google is, also Chrome, is looking into storing cookies in the TPM. I'm not sure if that's going to work out good, because as I said, like Chrome needs to have the secrets, right? But at least maybe you can have secrets that are very short-lived. And then you need to like be on the actual machine to be able to keep a token that works for a reasonable amount of time. But anyways, so that's sort of how we, that's the entire flow of the attack pretty much, right? So we see that the user called Devon in this example got a info stealer on the machine. That secrets that they dumped on his machine, including browser cookies, to GitLab, was uploaded to an initial access broker website. The threat actor acquired or bought the credentials from there, were able to log into GitLab. On GitLab, they were able to find a way to push or like run code inside Docker containers, which runs on the internal Jenkins machine as part of build jobs. They broke out of that Docker container over the network and got root access through the Jenkins console. Then they jumped to the internal Azure Active Directory sync server, and there they found the secrets, able to sync and create accounts and so on, which they abused to create that, take over that enterprise application, add credentials, and then enroll their own device and log in, and eventually they reached their target, which would be the, some interesting persons at the company. The other thing, which is kind of interesting, is that how do we know, I mean, it's always hard to know, like, how does it work with this, like, info stealers and the threat actor? Are they the same person? Are they different persons? How do we know that they didn't steal the credentials some other way? Well, in this case, they were very friendly and enrolled their device, right? So while we can't go back in time before they enrolled it and see that they bought these specific credentials, we can see them browsing Russian market, which is initial access web shop. So basically they did that Russian market, and then you see like these .edu, which they visited shortly after. So basically they're buying credentials and then they're jumping into different victims. So I think that's, I mean, it's not a perfect evidence for it, but I think it's a fairly strong evidence that they got access through an initial access broker. So I guess that's the attack. One final thing, this redline stealer, which it was in this specific case, we found that the malware was downloaded from this link. That doesn't look good. Right? Their competitors were really quick to point out that Microsoft's GitHub repo is compromised. They were very happy about it. But then someone at Bleeping Computer did some digging and figured out that, no, it's not compromised. This is an interesting feature in GitHub, which is that you can start an answer to a issue, you can attach a file, and then you can just discard that comment, and the file is still going to be there. And that file is going to be uploaded under the repo where you're creating the issue. So, I mean, this isn't great, right? I would download that Microsoft file and think that it's legitimate. GitHub did not think this is a vulnerability. They thought this was a feature. And with that said, I want to thank GitHub for hosting my documentation in their official documentation thingy. With that, thank you.
Thanks a lot for showing the incident. I wanted to ask, was there like any monitoring in place? Because like from the attack complexity or from the too many steps, it seems like a big company. So was there like any detections in the place? First question.
Yeah, absolutely. So keep in mind, this is a combination of attacks. I think there are like 3 different attacks which are kind of this scale that are combined into. So it's kind of hard to answer specifically because it would depend on which one I'm answering about. But one that comes to mind is an attack where that's very similar to this, all in all, in complexity and so on. The threat actor were able to, because they had access, like the compromised network infrastructure, so they could like sit there for quite some time and figure out which systems talk to the EDR. And then they picked the specific systems that did not use the EDR and jumped on those. So I mean, that would be one way. Then like it depends on what kind of detection capabilities that you have, right? So EDRs would see a lot what happens on the specific systems. If we take like that Gmail rat, it was based on, I can't remember, but an open source kind of sliver, you know, that kind of open source framework. But the EDR platforms aren't that great on Linux systems in general, and it was just undetected, basically. And network-wise, I don't know what kind of rule you would write to detect something talking to, you know, Slack if everyone is using Slack. It's really hard. Maybe you can analyze that it's a weird pattern. But then again, if you have like build jobs that are frequently, you know, talking to integrations, then yeah, it's gonna look weird. I mean, it's not only chat that you have there, right? So yeah, I mean, in short, yes, definitely had a SOC, had a bunch of them interesting capabilities in that sense. But yeah, I only see where the security operations fail, right?
Yeah, continue to this. Any of those incidents were triggered by alerts from SOC, or all of them were triggered by the ransomware or the whatever?
Yeah, it's none of these were ransomware attacks. It was more of a sophisticated actor. It's different. In some cases, it can be that the company is doing some hardening, and then they start hitting that hardening, and they're like, "Oh, that's weird. This VPC shouldn't block a bunch of whatever," right? In other cases, it's the national intelligence services that reach out to the customer and says that you need to check on this specific host name, and they're like, "How did they know the host name?" So that's kind of common as well. I guess you have a similar stuff in Germany where they can reach out if they have been tipped and so on. So yeah.
And more.
Thanks also from my side for this very interesting talk. I actually have 3 questions.
Yeah.
First of all, I wondered how the InfoSteal malware got on the system in the first place. Mm-hmm. Then I wondered how long did the whole analysis actually take you from a time perspective? And third, did the threat actor then also disconnect his device, or do you still have access or get telemetry data even by today?
Mm-hmm. So the first question, that would be that it starts with the code execution to these Docker containers that have network access. And then there's some kind of tunnel from that on-premises server up to Google Cloud. So that's basically how they got there. So they had sufficient credentials for that, basically in the environment secrets and so on. So they were able to connect up to that machine. But it can be a lot of different variants. The other question was how long. It's also like, keep in mind it's different cases, but one of them is like 2 years something from the start to the end, and we were the third company that investigated it. So it's like the first team that investigated it. They are a really, really good team, but I think that the customer gave them a too narrow scope, where it was like, you need to look how this specific thing happened. And they just did that, kind of, which means that they missed the rats and so on. So we see that, after the investigation, they reset a bunch of credentials, and then 2 days later, the threat actor dumped the entire Jenkins machine again, and they have all credentials just as nothing happened. So, so for that reason, and that the threat actor didn't really stress, they were more interested in keeping access, so installing a bunch of sneaky persistence and all of that, and focus on keeping the access more than we need this access now, kind of. The investigation is usually quite fast. The attack is usually very long. I guess is the short answer. What was the third question? I forgot. I don't know actually. I think they disconnected it. So it's one of our customers, right? So I sort of just got a export CSV from. By the way, guys, you probably want to see this. So I don't know, man. I'm pretty sure that they disconnected it by now. So it was like, I sort of touched upon it, but it's 3 different investigations, right? But it can be anything from but I would say around a month maybe, from first start of the investigation until the report is done, kind of. But then it varies quite a lot between the different, from the customer's perspective, we were said the third company in that case. So from their perspective, they had to sort of battle this for the last 2 years, kind of, right? Since the first thing started. But it varies a lot. In some cases, like in ransomware cases, it can be I don't know, a week or something, where it's pretty fast because they aren't that sophisticated and they aren't using, they're literally installing any desk for C2 because, it's actually pretty clever, right? Because no AV detects a legitimate remote access tool. But it's kind of easy when you do a forensic investigation because there's literally a log of all the connections. So it's, so it varies a lot about the length and the complexity of the investigation. One of the things that makes it vary is also if we want to do a stealthy investigation, because maybe we don't want to alert the threat actor that we're on to them, and then you use more stealthy methods, where if it's ransomware, then everything is just encrypted, right? And the threat actor knows that they know, so we don't need to hide. We just need to hurry up to make sure that they get back again and know what backdoors to remove and so on. So yeah. Mm-hmm. Yeah, absolutely. But do you mean to share or? You mean like that? Yeah. Yeah, absolutely. So that is a major challenge, of course. So, imagine doing this investigation and it, patient 0 was 2 years ago. So in many cases, some server that they compromised has just been reinstalled for whatever reason and it doesn't exist anymore. And retention is really short, right? But you sort of, there's a lot of things that stay over longer time as well, right? So It can be like deleted files might still be there. It can be some kind of logs are usually also in the backups. So if you restore backups from that date, maybe you're lucky and they still have the artifacts that was there 2 years ago. And yeah, it's obviously delays the investigation quite a lot because you need to work really hard just to get a simple log. But usually we try to and succeed to figure out where to get the evidence that we need. But yeah, I would prefer if everyone started detecting the attack the day after. That would make my life easier.
Do we have any more questions? All right, well, thank you.
Thank you.
Thank you so much, Alexander. So we are now at the last part of the con. Of the talks, we'd like to thank everybody, our sponsors, our vendors, our speakers, of course, the Goethe University, our lighting guys, sound, and everybody, and all of you, our beloved attendees, for taking time from your hectic schedule to come here and enjoy this conference with us. Thank you all so much. Of course, and also our team, the BSidesFrankfurt team, my fellow colleagues, thank you so much. And of course, this won't be possible with our two grooviest founders and organizers, Alex and Christine. Thank you.
Thank you, guys. Yeah, so, Alex, no, you first, you first. Yeah, wanted to thank you all for being here again. Thank you to our sponsors, our volunteers, all the speakers, and also we want to thank Hacker School for providing the devices for the kids track. My kids were here, they really enjoyed it. If you got your kids here, I hope they also enjoyed it. Yeah, I think we should have another round of applause for Alex because he did most of the work. So thanks again, Alex.
Yeah, unneeded. Thank you. I want to thank you, all of you. You came here, as I said, on a Saturday. Most of you in the private term. It's 30 degrees, you stayed here, I don't know. It feels warm for me, maybe because I'm stressed, but thank you for staying. Thanks again, sponsors, the speakers came from Sweden, United States, all the way, did it volunteered. And I don't know, Kids Track was fine too. Thanks for all the helpers. You as well, Patrick, so all of them, Alex. I would encourage you, it ends, but it's not over yet, to network, grab someone. I don't know, I will go and have a drink and dinner, grab someone. If you need to connect to someone, meet down at the lobby. Rita says, follow Rita, or someone with the t-shirts maybe. I need to join later, but if you need help, ask, and yeah, I encourage you, go network, talk, and exchange, and thanks so much for joining.
Thank you, guys.